So I guess I'll start out again, always. Oh, good morning. What does anybody have any questions they want to, or anything they want to raise? Okay, so you guys can see this. I uploaded the slides, by the way, just now. So today we're at September 17th. So today we're going to do storage, and we're going to cover in lecture storage and indexes. And I'm going to probably go through this fairly rapidly. So I might just want to get down to it very quickly here. Next Tuesday, then, we're going to do query processing. So this is going to be how you use the indexes and kind of other factors, and how you can make it so that your queries run very quickly, which is always good. And then next Friday, so exactly 1 week, we want to have project meetings. It doesn't mean you have to have an approved project yet, but I definitely want the groups. So I want a report of exactly who the groups are by next Tuesday. I know there have been some issues about some people, like I guess it was a person who left the course, and it brought one of the groups down to 3 members. Let's try to have 4 members per group. But if yeah, so right here, I'm in need of a group if anyone has a spot. So yeah, so if you have only 3 members in your group, then it looks like Max here is at least one person you could bring in. So I'd like to get them at 4 if possible, but I realize that in the final analysis, it might be there might be a couple that are 3. I don't want to go down to 2 though. I mean, I want you guys to get a group experience on the projects. Okay, so that's that. So then we're going to have those project meetings, and then we're going to have the second recitation on this query indexing or query optimization in recitation 2. So this recitation number 2 will release on Tuesday. Okay, so are there any questions? I mean, it feels like things are kind of cruising along in the course. So, but let me know if anybody's got any issues, and I can address them. You can also just send me private chat or whatever. Okay, good. Looks like this group thing is being resolved. All right, so let's get into this. Let's get into storage. And let me just start this puppy out with a full presentation mode. Let me see here. Okay. And there we are. So storage for database systems. All right, so this could be more, I mean, this is, well, it's kind of obvious that one of the first things, you're going to have a big database, you're going to have any database. The first issue is that, well, it's got to sit somewhere, right? And it's got to sit somewhere persistently. So in other words, if the power goes out and you then restart the power, you want the database to be there. So it can't sit just in main memory. It's got to sit on some file system. So what does that mean? It means that a file system, okay, so basically it has to sit on secondary storage, right? It can't be in primary storage that gets zapped when the power goes off. So basically that means it's either going to be either be sitting on a disk somewhere, or it's going to be sitting on a SSD, okay? Okay, a solid state device, a solid state drive. Just out of curiosity, how many people have, okay, if I ask how many people have laptops, I'm assuming everybody has a laptop here. I mean, it's just an assumption. Maybe it's not true. But for those people who do have a laptop, how many people have a spinning disk, and how many people have an SSD? Is just let's see. Let me see. Let's see if I can. I'm just kind of curious about what people have. Okay, some people have both. I just have an SSD, so I've kind of gone over to the new way, and both SSD, yeah. So every time I do this, I mean, I used to ask this question years ago, and the answer was always like, well, mostly hard drives, but I mean, SSDs are taking over. Now, the thing is that when we look at stuff like, let's say we have a big database that you're going to be working on with a team and all that. So let's be honest. I mean, it's going to wind up on a cloud device. It's going to wind up on a cloud account. All right, it's going to be, you're going to do it through like something like Amazon or something like this. I mean, that's kind of standard practice these days. I mean, no one maintains their own hardware anymore. I mean, if they are, it's a bit special. Okay, some places do actually have their own on-premise kind of site, but most, I don't know. I mean, it's definitely the fashion these days to kind of to go with something like AWS. So they have both disks and SSDs that can back back their storage. So so the disks are still, I guess what I'm trying to say here is that disks are still alive. I mean, we still have disks, and there's some good reasons for that. All right, this is kind of standard stuff. So when you see like when people write down these things, when you see a little b, that means bits. So that's usually has to do with like transfer speeds. And then big B is bytes. And then of course we have kilo, mega, giga, and tera. And then what do we have after tera? People must know this. I mean, we have peta, which comes after tera. And then I have a exa. So we have tera, peta, exa, zeta, and then finally we have yotta bytes, which I think are 10, or which are basically I think 10 to the 80th power in that, well, in a binary thing. Okay, so so let's see here. So 1 kilobyte means 2 to the 10th, and then if you take 1,000 times 1,000, you get a million, which basically means that it's like 2 to the 10th times 2 to the 10th is 2 to the 10 plus 10, which is 2 to the 20th, right? So if I basically I want to just, you guys know this little trick. If I ask you what is 2 raised to the 25th, 2 raised to the 25th, I'll put it in the chat here. What is that very quickly? So you should be really fast with these things, okay? So what the trick is basically this: if it's 2, so you first basically, that equals, this equals 2, oh, damn it, 2 raised to the 20th, which is a, that right there is a million, right? And then 2 raised to the 5th is 32, so it's 32 million. So 2 raised to the 5th, oh, actually it did work there. All right, anyways, that worked. So 2 to the 20th, right? Okay, so really, if somebody says, okay, what's 2 to the 36th? Well, what's 2 to the 6th? That's 64. And then I said 30, so that's a billion. So that's like what I said to the 26th. Well, 64 gigs, I believe is what that is. Okay, 64 billion. All right, is that clear to people? That little trick. I mean, you guys do know all your if you know all of your 2 raised to the up to 10. So what's, okay? You should, as a computer scientist, you should absolutely know what is 2 raised to the 6th. 64. Boom. What's 2 raised to the 5th? 32. What's 2 raised to the 7th? All right. 8th, 9th. Okay. 9th is 512. All right. So so you'll be able to kind of pick these things apart. So it's kind of a nice trick to have up your sleeve. All right. Yeah. So when you go from bits to bytes, usually for data, because there's overheads on data transfer, you will instead of dividing by 8, you'll or instead of dividing by 8 to get the number of bytes, you'll divide by 10. Okay, so basically what this would mean is if you have if you know you can transfer at 3 gigabits, right? So lowercase is for bits a second. That means you can transfer 300 megabytes per second because of this kind of rule of 10 rather than 8. Okay, but it's kind of handy, but it accounts for the overhead. All right, so I'm sure you guys have seen this before. We have basically the memory hierarchy, and this will never go away. I mean, this will always be present at one level or another in computing. There will always be a memory hierarchy of one form or another. We might eventually knock out the mechanical disks, because remember, a disk. The problem with the disk is it's got a spinning device, and that's not what we really would like is to make everything so that we don't have physical movement as a constraint. It's all electronics. That's what the goal is. But we still have this kind of rotating disk down there. But even once we do get rid of that, then we'll still have. I mean, let's say, for instance, I mean, why do we still have magnetic disks rather than, and not everything's just an SSD? The reason is, what is the cost? The cost per unit of storage. So as you go further down here, the cost per unit of storage, of course, descends, and so it is still like per gigabyte. It costs less, or per megabyte, It costs less to store something on magnetic disk than it does on an SSD. If it ever turned, if it ever became like the same price or even cheaper with an SSD, then magnetic disks, that's the day that magnetic disks are just completely legacy and going to be replaced, right? Because why would anybody buy them at that point? There are some exceptions like optical disks because of the carrying capability, because you can carry the thing physically. But even those, I mean, who uses CD, DVDs, or Blu-rays anymore? I guess some people. I mean, but I guess people do with like PlayStation. Some people like to have like the actual disc. Maybe, I don't know why, but maybe because they feel like they own the game or something. I don't know. But it's kind of stupid actually to do that, because the thing is, if PlayStation is spinning that thing, then the fan has to run more. So really, I mean, yeah, for your PlayStation, not that you guys do play PlayStation, you wouldn't do that. Putting it on bringing it down rather than having the actual disc might be smarter in terms of not being annoyed by the fan. All right. Okay. Any questions here? No. All right. Moving on. So for databases, though, we're going to mostly focus just on this simple model here, where we have RAM. You have different levels of RAM. So there's also the whole issue, and this will happen in the future. That is that we have the whole hierarchy between the cache memory inside the central processing unit, and then the actual RAM memory. But for now, what we do is we stick with the same old model of, we either have things that are sitting in RAM, random access memory, or we have things out on disk. Okay, so obviously, what you would like when you think about it from a database point of view is you like the database processor to have it's much more costly to go out to disk to fetch data than it is to actually just get it in RAM. So it's a big optimization problem, or an anticipation problem, or a scheduling problem to keep what you need in main memory. That's the goal. Of course, keep this in mind. The problem with main memory is that someone can pull the plug. I mean, you can have, if you have the whole database sitting in main memory, that's great. It's very, very fast. But what happens, you're making out all these updates to it. It's fine. Let's say it's financial data. You make all these updates to it. And then let's say that Jones winds up tripping over the power cable and pulling it out of the wall to the database. Then boom, it goes down, and then poof, you've lost all your transactions. So you need to always be writing stuff back to disk, back to permanent storage. So you'll always have a disk, especially when you're doing lots of updates. You're always going to have the disk involved. All right. Difference between static and dynamic RAM. So I think it's just a technical difference. I'm not much of a hardware guy, ultimately. I know that there's a whole bunch of different types of RAMs that you can buy. And I believe, it's probably somebody knows better. You can put it in the chat if you know better. But my understanding is that the static RAM is faster, so you can actually access it much quicker, and it's just kind of a special type of RAM that you can have in your system. So it's more expensive though, of course, and then also there's the whole issue of registers inside the actual central processing unit, and so it might also that's probably a type of static RAM. But I don't know so much about that. I haven't really done much physically with. I used to build my own computers, but I haven't done much physically with them lately. I have some vague recollection of putting in, but I think that back then it was just a standard dynamic RAM. All right, but if anybody knows, then yeah, you can look it up though. But it's all right. So, anyways, our primary thing is we just kind of, from the database point of view, we're going to assume that there's RAM and then there's a disk. Okay, those are the. Okay, so yeah, so you can have all your, I think probably I alluded to this a second ago, you can have all of your whole database. In some cases, you can have the whole database sitting in main memory. All right, so this is especially true with databases that aren't that big and that are read-only. So in other words, you're just bringing the data, you have the data up there, maybe you update it offline or as a special process. But most of the use cases, it's just it being queried. That you definitely want to put into main memory if it can fit, because then it'll be really, really fast. Okay. Let me move this thing. This is in the way. Get that away. Okay. All right. So solid state drives are impacting more and more databases. So when I put a database on my laptop here, actually the model is different than the spinning disk model. The model is that, okay, I have main memory and I have my SSD device where my whole file system is my whole file system is on my SSD. So when it goes off to get stuff from the SSD, it's doing it as a random acts. It's doing it. It's randomly accessing the SSD. There's no spinning parts. There's no waiting. And we'll talk a little bit about how a disk is modeled. So what this ultimately does, and what we'll ultimately see is what this does is this makes a certain type of indexing much more feasible on SSD databases. And that basically says that we're going to talk about them later. We talk about secondary indexes. Secondary indexes in a traditional disk-based database are really not so great. But if you but on the SSD, they're great. Okay, so what SSDs really do ultimately is they enable a certain type of indexing or over-indexing, if you will, of your data. So it's really it's had a profound effect on the feasibility of building many, many indexes over your data. Okay, so it's quite good. Now let's see here. Was that even mentioned here? I don't think so. But basically, what we're talking about here is we're just talking about the fact that they have not completely replaced hard disks yet, but that probably will happen at one point in the somewhat near future. I don't know. When will we finally get rid of disks? 3 or 4 years from now, maybe? I don't know. Just a guess. But we will. Disks will. There's not much of a future in the spinning disks. Okay. So mechanical hard drives are much slower than dynamic RAM or SSDs for that matter. For random access, it's typically 1,000 to 10,000 times. Random access memory is typically 1,000 to 10,000 times faster than a hard disk. So, for instance, if you have everything in memory and you say, give me that particular record, the speed at which you would do that, if it was all sitting in main memory, would be about 1,000 to 10,000, 4 to 5 orders of magnitude faster, because if you do it that way, then you just get it. But if it was a disk, what you have to do is you have to say, hey, disk, you got to call in and you got to wait for the disk to rotate so that the sector of where that data is located is under the reading head. And this thing is only rotating so fast. So we already have an eon of time for it to kind of go underneath the head. Then it's got to be read and then shunted into main memory. Okay, so that takes forever and an eon. Compared to just grabbing it from your memory. All right. Okay, so let's just talk a little bit. I mean, I don't want to go into this too much since they are ultimately, this is not going to be relevant because we're going to be done with these soon enough. But basically, you have the notion of a sector. I don't know if you guys can see. You can see my pointer, I'm assuming. You have the idea of a sector, which is this right here. This corresponds or is some multiple of, a block. What we're going to be talking about when ultimately is what we're going to call blocks. All right. So it's all going to come down to what are called a block. And a block is let's just say that there's a 1-to-1 correspondence between this is just kind of an assumption, 1-to-1 correspondence between a sector and a block. All right. So if you want one particular block of data, then you have to get to the sector on the disk, and you have to snarfle it up, or you have to read it. Okay, I say snarfle means that when the head reads the sector. All right, so it has to wait for it to spin underneath the assembly here. So yeah, so these disks, I mean, if you crack them open, it's kind of interesting. Actually, I remember one time, for some reason or another, one was busted open. I think it was at the junkyard or something. But yeah, you can see this if you look at one of these disks. So you have this ARM assembly here, which you have these spinning platters, and then each of these is a platter. Then you have a track, which is the whole area it spins over, and then you have a sector, which is kind of a little piece of that track. And then you have the head. Well, read here. Now, when you have a head crash, which I'm sure that we've all experienced or heard of at least, it's when this thing right here runs into the media itself, and it all kind of just gets ruined because the thing's spinning very fast. And so if this thing is kind of off by a little bit, what it does is it scrapes the hell out of everything. You can still crack it open and reconstitute it if you're like the FBI or something, kind of grab the data you want, but it's a big operation. All right. These are just some kind of physical, dimensions of it. So if you want to kind of get into the modeling, you can. So what we have here is we have the notion of we have two mechanical pieces that have to move. So you have the reading head. So you have the platters that are all spinning. And you have the seek time, which is the time it takes to move the head over the right track where it's going to pull in the data. Okay, this is just if you say, let's say I have 20 million blocks that constitute my database, and I say, give me block number 499. Right? So it's going to say, oh, block 499. I have to move. First, I have to seek. So I have to move the assembly, the reading assembly, over so that 449 is in the, on one of my reading, one of the platters, there's a track, and 499 is on that track in one of the sectors. So the seek time is first to bring that assembly over, and then we have to wait for it to rotate around so we can snarfle it up. And so basically what you wind up having the seek time plus the rotational latency. All right, and both of these are governed by a physical process, right? In the case of moving back and forth, the read write heads, and the other one of just rotating the disk around. So that's bad that they're mechanical. We ultimately want to get away from that. So you can do a calculation here. You can see that it is a significant amount of time. All right, and then the thing is also is that when you look at, some things are getting better in the world, like the density of data on the medium. On the media, I think that's kind of undergoing some kind of Moore's law type, some doubling every 11 months or whatever it might be. On the actual media on the platter that's accepting the charges, that is getting innovated. But the speed at which the head assembly goes back and forth, or the speed at which the disk rotates, those are essentially constant. There's really no improvement to speak of with those. They've kind of reached the limits on what can be done. All right. So that's one of the things that kind of means that these things aren't really, getting much better. All right. So as you can imagine, you can do a lot to kind of to play around with ways of laying things out on disk. Now, when you buy, like for instance, if you're a bank and you buy an Oracle machine, I think I have a brochure somewhere for the Oracle machine. So Oracle just basically, they have their own operating system. They have control of everything, even down to the hardware of how it does the disk access. So if you really are serious, you go and you buy one of those, and it really squeezes every bit of performance out of the system. But us who don't do that, and lots of other people, we have a situation where we have our normal file system, running Linux or something, or even something worse like Windows. And so what we have is like Linux manages those devices, all right. And then the database just reserves like some space on, but it uses like the underlying operating system commands or underlying operating system mechanism and code. System, the underlying operating system, to manage like the transfer of blocks in and out of, in from the SSD or in from the disk and out. All right. So, okay. Now I don't want to spend too much time on this because again, it's just kind of an issue of us getting things done here. But how many of you guys have ever configured a RAID? Anybody? So RAIDs. So basically, this is one of these things. It's good to know a little bit about this, and it still is relevant in the cloud computing era because you can actually go in and especially with like AWS, you can go in and you can configure for different RAID levels if you want to, like if you're really. But this is really kind of when you have a performance problem with your database, this is not where you want to start. You want to start with some stuff that we'll cover a little bit later because this right here, I don't know how much you're really going to get out of it. But the basic idea behind RAIDing, or it's redundant arrays of inexpensive disk or redundant array of independent disk. So the goal. So basically, what RAID involves, there's basically two ideas, right? Replication of the same data over several drives gives you redundancy. So if there's always a probability that some hard drive is going to bust, then you want to make sure that you could say this. You could say that there's a problem. Each hard drive is carrying an independent probability of failure at any moment. Okay, You run these things for 5 or 10 years and they will fail. I mean, they will have a media crash. Okay, they'll break. So if you have a system in which you're going to have multiple, you don't want to lose any data at all. And so what you want is you want to have redundancy. So you want to, when you write something out to disk, you want to write it to 2 disks, or you want it to write it to different, 2 different spots. You want to write to many different spots. You want to have it so that the probability that you lose anything is lower and lower. Now that assumes that there's independent probability that the disks fail, but that's probably not true actually. So for instance, if I have one computer system and I have 2 disks on it, and I'm writing everything to both those disks, that there is one probability that, there's a probability that each of the disks will just, break. Okay. And then if one of them breaks, then at least I have a copy on the other one, so I didn't lose any data, right? But there is that kind of independent within the hard drive itself, there's a probability of it breaking, but there's also just like kind of the common sense thing that says, well, what if someone tosses a grenade onto the computer? And a grenade is going to knock out both hard drives at once, right? And so that's the kind of the probability of it's not independent. If grenades are flying around, then the probability that if a grenade lands on the computer, it's going to kill both hard drives. Okay, so a raid won't help you. I'm trying to say. We can talk a little bit about some other kind of things, like maybe if you look at let's get a little more realistic here. Let's say that you have some data that you absolutely cannot lose, right? So you might say we can never lose this data. So once we get an update that comes into the database, it had better exist on multiple disks and at multiple locations, right? So you can actually configure this on Amazon, which is very nice and one of the big use cases for Amazon. And this is like, back in the day, you would have companies like these big multinationals who would have all of their own resources. So what they would do is they would build these things where when they made updates to the database, they would sync them essentially across different, physical localities. So you might have you're going to get one copy in Japan, you get one copy in California. And other than like full thermonuclear war, there's not much of a chance that both California and Japan are going to get zapped. Okay. And if it's full thermonuclear exchange, then who really cares? I mean, I don't know. But in Amazon, you can actually configure this very easily. You can have it so that your data is being replicated across multiple of their availability zones. So you could absolutely have Japan and California. You essentially could guarantee that you're never going to lose your data. All right. So, if a giant asteroid slams into the Earth, then you're going to lose your data. Okay. All right. Let's see here. So that's one aspect of using a RAID, where you kind of have it so you can have redundancy. So if disks fail, and then there's another thing, kind of orthogonal kind of consideration or use, and that is it's not really orthogonal, but it's a different idea. That is to speed up access through striping. Okay, so let's just see if we can show kind of what this means here. So one idea here is, let's say that I have let's say I have 1,000 blocks in my database, and I always put I do mod 4. So whatever block 744 mod 4, that will determine which of these hard drives it's going to be on. So the block right after that will be on the next hard drive. Okay. So what that means, then it means that if I need to read all those blocks into main memory, I can have it so that I can get a factor of 4 speed up, right? Because I'm basically going to be having 4 times the amount of blocks coming in as I scan through the file. All right. So the striping gives you enormous speed ups in terms of reading. All right. Does that make sense? Okay. So anyways, this business of setting up RAIDs to kind of do that, there's one that's kind of, so you have replication as type 1, and you have 0 is for striping. So a pure 0 approach to RAID will give you, so that you basically, what you want to do is you stripe across the 4 disks. And then a replication one means that you're making a copy of all the blocks across all the 4 disks. So these are 2 different ways of doing it. Now, what databases do is they combine them both. So what this means is, it means every other block, you're striping and you're also doing replication. Okay, so striping and replication, and that's a type 10 RAID. So this type 10 RAID is actually what will default on Amazon. So this type 10 rating is what you kind of get by default. So it's, I mean, I suppose my own desktop here, when I have my data, my database and all that, I'm not using any RAID at all. I just have one device and I'm not doing any type of rating across it. But you'll get kind of rating as kind of a normal kind of, you'll normally get it set to 10, and that's usually what we do in databases. So what that means basically is it means you can knock out, so if I knock out, so which combinations, let's say that we lose any one of the disks. If we lose any one of the disks, we can always recover everything, right? Because we have the redundancy. If we lose like disk 1 and disk 3, then we can still recover everything because we have, you know, the stripe. We get, basically it's a good balance between the two types. So 10 is usually the one that's used. But if you want, so let's see, so the amount of redundancy is chosen to meet the need level since redundancy is okay. So that, all right. I'm not going to say anything more about RAID, but if you're interested, and it is kind of interesting in its way, you can go in to AWS and you can, so there's certain types of RAIDs where you're doing parity checks. You can really kind of, you can really wind up getting really major performance boosts, or while keeping some level of redundancy, and you can have it so that you can, like, basically the probability that you're going to lose any data is really, really low. You can fiddle around with RAID, but I'm not really sure how many people do that as a practical matter. RAID 10 is kind of done for databases, so I don't think there's a lot of database work that's maybe for really big organizations and really special cases where you'll monkey with the RAIDs, but I think for the most part it's just RAID 10. All right, no questions? No. Ooh, coffee. All right. All right, this is kind of a subtle point. All right, this is important here. So we have that ultimately okay, so when I was telling you guys before that you can buy an Oracle machine, and that machine is basically giving a raw disk access. So you have using a very, very low level interface to the OS. I'm sure that the Oracle machine has some variant of Unix or Linux that is at its base, but the database itself is integrated at a very, very low level. And most commercial databases do this to really squeeze performance out. So they're bypassing the OS, but it makes it so they're not very portable. So when you're talking about you know, the portability issue, it becomes very, very particular to that particular hardware platform. So it's very native. Yeah, you can, if you screw up the installation, you can maybe, if you have, I mean, so generally, when you talk about these kind of machines where you have a commercial system and you're talking about the installation and the configuration of that, I know that, like, I remember hearing the story of this professor that had got his research group had gotten Oracle to give them a full, you know, they were going to do the for real Oracle installation, but they never could succeed at doing it. They tried and they tried. And then it turned out that Oracle wanted to send them to Oracle school to show them actually how you install the thing. So it becomes a kind of a revenue model for the big commercial databases. But it was, let's put it this way, there's some really very highly intelligent systems people, and they could not, by just reading the manual, they could not install the thing. And, you know, they weren't proud of that, but they couldn't do it and they gave up. But Oracle was going to rescue them by sending them to Oracle school, but they didn't have the revenue to, I mean, it was a bit of a problem there, but I don't know exactly what happened in the story, but I guess what the point is that you would hear this, basically people say, oh, don't try even to install Oracle because it's impossible. But that is in a particular case where you're installing it using their operating system. But if you're installing Oracle over Windows, that's easy, right? But then that's using the is letting the operating system do the managing of the files. So one of the problems with that is the double buffering problem. So basically what happens is that the OS, so the operating, so you have the operating system says, oh, I want to bring in this file, and so then it manages bringing in the file into like somewhere in main memory or something, and then it may be that it gets copied again when the database system wants to use it. So you get this kind of two buffers might possibly get occupied. So it becomes a systems issue. I mean, there's a reason why you would prefer just to go to the lowest level, but as a practical matter, most of the time you're doing this. But the doubling buffering problem is mostly avoided. I think that, but it can be something that might happen down in the guts of the system, something to keep your eye out for. That two copies might ultimately be two copies of the data might be being maintained. One hopes that doesn't happen, but it's possible that in certain cases it'll happen. Okay, so that's storage. Is there anything else I want to say about storage? Is there anything that you guys want to ask? I think the thing to keep in mind is that this has all changed now that we've gone to cloud. So everything's being done in the cloud. And moreover, it depends. I mean, if you use Amazon, they have their own RDS system. So they have their own service where they actually manage all this for you. And you can just basically have a database server, and they will manage that for you, and then do all the updates, all the security stuff. So I think that a lot of businesses, when they do a database on the cloud, they use one of these services like RDS, so that this stuff gets managed. I guess I'm not sure how many of you guys have done anything with AWS, but you have Azure now, and you have the Google Cloud. You have these other clouds, but I think AWS is still kind of the king of the cloud. So on AWS, you can also, I mean, you can play around with buckets on AWS, so where you actually just get chunks of storage space, and then you can kind of play with those. And then there's the Elastic file system. There's lots of different options with it, I mean, when it comes to it. But I think that, and then you have also the whole kind of idea of the data lakes. So AWS has done some really, really kind of interesting stuff, actually, in terms of like giving like SQL type access to a file system thing. It's called, I believe it's called Select in AWS. And maybe we'll get a chance to talk a little bit about that later. But anyways, this stuff, for the most part, it's just, just kind of you get space. Okay, so now let's get more into databases, though. Let's talk about the physical organization of data. Now, I do not want to do that, or do I? Oh, sure, why not? Not really, no. I'm gonna do it the old-fashioned here. Oh, get away. In fact, I'll just kill that, and I'll go here to physical. Now we can talk about this. I'll start this out, and I'll just try to find a good place to take a break. But let's see here. For now, let's just gotta keep on going. All right, so as you guys know, there's this notion of data independence. So what this basically has to do, it has to do with the fact that, I mean, we have the notion that basically you don't really know how the tables are being implemented in relational databases. I mean, different vendors will do it differently. So the decision as to how to physically organize stuff actually on the disk is kind of independent of the SQL view you're given of the database. Okay, so that means that and this independence is kind of like really part of the system. Now this is really a great benefit of the relational model, because now what allows for is from the point of view of using SQL, you don't see any difference. I mean, your select queries and everything else kind of does the same. It gives you the same exact results, but there's a lot of freedom of how it's actually going to get physically implemented on the disk, and the access methods, and the internal system. There's a lot of freedom there, so you can really kind of I mean, the thing is that let me just back off here and let's talk a little more kind of philosophically here. Why, if you think about it, like, let's say that you're building a system, right? And you know that, like, I mean, what I'm saying here is kind of, you might say this is kind of stupid, what Michael's saying here. It's kind of like, yeah, no, duh, that's obvious. But I want to kind of just remind people of it because it's kind of an important point. Let's say that we're all going to build a system. We put like 40 programmers together, and we're not very good management, and we just kind of say, oh, we want to build, and we kind of describe this big system. That's going to be a disaster, because what's going to happen is that everybody's going to kind of go off, but all their stuff has to talk to one another, but no one has firm definitions over what they're doing. So it's essentially, if you can say that you can throw a whole bunch of money at a group like that, and maybe like some little skunk works of 2 or 3 really good developers will kind of break off, and they'll actually build a whole system themselves, while all these other people are like tearing each other's hair out and attacking each other around the water cooler. So they'll actually do it right because they, are smart and they kind of talk really, but they keep a small group and they keep it very tight, and they can build something kind of that really makes sense. Whereas the giant group, you add more people. And I mean, that's the kind of thing, like if you're going to build a bridge, a lot of times it helps if you just kind of add more labor in, you can speed up the process. When you're going to build software, it doesn't work that way. You add more people. Sometimes when you add more people in, you just cause more problems in the groups or you actually destroy the productivity of the whole group by adding more people to it, right? I mean, this is one of the problems with software. But if you look at a system, let's say that you build a system though, and you think, oh my God, I mean, if you look at how many programs were involved in building this particular system, well, you have to include all like the kind of C programmers who built basic Linux, because the system is running on top of Linux. I mean, you have potentially hundreds of thousands of programmers who actually contributed to it. But the reason why they were actually able to do that is because people are doing things over clear, like API boundaries, where they don't care, or it doesn't matter, it's irrelevant as to what's going on underneath. It might affect performance though, but it doesn't affect the logical view of what it is that it's producing. Now, the reason why that can work in systems is because these things have matured, and kind of like no one's going and changing underlying Linux. If they were, they would be a disaster. We wouldn't, if somebody comes off and they say, well, we should change LS to LLS or something, it's like, shut up, don't touch it. So much depends on that, so don't touch it. So like this, you get this naturally through time, you get this kind of stratification of the systems levels and the shells of the systems, so that it doesn't matter, so that basically you can use all this great work that people have done before, but you don't have to like talk to them or deal with them. I mean, you just kind of see the interface. So the same is true over a relational database, is what I'm trying to say. So this physical data independence basically means that somebody can switch around the implementation inside the database. You don't even have to know anything about it. And then all of a sudden performance is much better, but you still have the same SQL view, okay? I mean, if they say we want to change SQL in some ways, maybe extend it, but if we want to like get rid of something that we were already depending on, the answer is no. Everything has to be backward compatible. Okay, so that was kind of an obvious thing, but I just wanted to kind of, sing the praises of that kind of, this kind of like physical data independence, or this kind of idea of hiding things behind interfaces. Now, if we really look at it, there are basically, when we look at access, we look at the types of access we're going to have into a table. So just consider a table. What are the basic types of access that we're going to have? So what basically we can have is, they basically break down into 3 different types of access. We have key-based access, which is retrieval of data based on the values of a specific key, okay? So that would be something like saying, give me the data for this particular persona number. That's the key, right? Give me the data for, and then you get the persona number, it goes in, it finds that record, and it brings it up, okay? That's key-based access, all right? Another possible one is that we have sequential processing. So retrieval of a large amount of data in some order, basically it would be something like, sequential processing might be like something like this. It would be something like, I want us to retrieve the data in the order. So give me all this, we have all this data, and I say, give me the data ordered by, let's say salary or something, from highest to lowest, right? So that's basically a sequential processing type task. So it's like saying, give me an ordering over the data, right? So that would be something like, yeah, like that one, what I just mentioned. Okay, so that's another possibility. All right, so we say give us something in a certain order. Give us a particular key, give us something in a certain order, and then we have range queries. So retrieval of data, which certain parameters fall within a range of values. So then I would say, give me like the people with the, give me the people with the salaries between this particular amount and this particular amount, right? So that's a range query. So these are, we'll come back to these again. We have key-based, we have sequential processing-based, and we have range queries. And then of course, any particular query might have a mix of these. It might have a mix of these kind of things. So for instance, if we say something like, so if I say, so give me the people in Umeå, give me the people in the database that live in Umeå. That is key-based, because what it's saying is it's saying that we're going to set the value of their city to Umeå. And then if you say something like, we want people that live in Umeå between this salary and this other salary, then that's a mix of key-based and sequential. If we say we want the people that live in Umeå between this and this salary, and we want it ordered by how old they are, then that's a mix of all three of these. All right. So is there any other type? I mean, I don't think that there's really any other type of condition. I think these cover pretty much everything. That these are the types of base queries that everything's based on. So keep that in mind. Those are the types of access. And I think now this is probably a good time for us to take our break and be back at 15 after. Let's see what do we have here for time. Yeah, let's get back at 11:15 so we can hopefully finish this today. Well, we'll see. And put any questions in the chat or yeah. Okay, so let's take a break and then we'll be back at 15 after. And I will have to figure out how I can pause the record. Okay, I'm assuming that everybody's back now. Kind of want to get into this. What time do we have exactly here? Because I did promise that I would do it at 15 after. Let me see here. Yeah. Wait. Okay. Good. Right. Okay. So this way. Okay. So let's get going here. So yeah. All right. So what we're going to cover here is the standard row store. So PostgreSQL, all the standard transactional databases, they do a row store. Things like like Redshift is an example on AWS. They give a SQL interface, same thing as PostgreSQL it looks like, but underneath the hood they're doing a column store, which is much more suited for data warehousing type queries. You get really good speed ups that way. So that again showing the physical data independence. So the same SQL, but underneath the hood implemented differently. In this case, we're going to look at the classic row-based implementation. So you take an example here where we have like a department here with a name, a building, budget. So when you look actually at how things are being organized on disk, or how things are being organized, written on disk, I'll just say disk, but you could be an SSD as well. What you'll see that actually like the first 21 bytes are going to be the department name, followed by 16 bytes for the building, then budget, and then it will go on to the next record. Okay, so that's how it's going to wind up being stored, each record. So these are fixed length records because there's no something like a text, right? Like a typed text here would be like a character large object. And so actually what gets stored inside the record for those is just a pointer out to some heap where the actual file is. Okay, so you can make it so that that you can have a fixed width for each of the records, right? And so the way you account for that, again, when you have these character large objects, is just a pointer out to some other place that manages the the actual contents of that file. All right, I hope that made sense. So fixed length records is kind of the standard way. So now blocks. Now we're going to talk about blocks. So a block is going to be the unit that goes get that it's like in operating systems it corresponds to a page. So sometimes you'll hear a page and block used interchange those two. But I'm going to try to stick with just saying block. So in databases we're talking blocks. All right. So a block is like this fixed size, and inside the blocks we can have multiple number of records. So when I go out to disk, I say give me a particular block, and it brings in all the records in that block. So so records are stored in these blocks, and a block is usually corresponds to a sector size on the hard disk or a small multiple of that size. So the standard block, like the default block size in PostgreSQL. So when you guys use PostgreSQL right out of the box, it's 8 kilobytes. So you have 8K size blocks. That's how big it is. All right. Now you can configure that. You can change that. You can go up to high as 32 K blocks, or down to maybe even just like 1K block. I'm not sure how small you can make the blocks, but you can vary that. But just think 8K is your standard block size for PostgreSQL. All right. Now the blocking factor is the number of records of a particular table that you can fit inside of a block. So we always break things into separate tables. So we're going to say, okay, the customer table, we're going to organize that. That's going to occupy a certain number of blocks on the hard disk. All right. So for the customer table, what is the blocking factor? And the blocking factor is how many records can you stuff inside of a block. All right. So PostgreSQL and almost all databases will never span records to save that little bit of extra space. They want to keep the implementation simple. So there's always going to be a little bit of slop left over. So for instance, if I have let's say that I had, just to keep it really simple here, let's say that I had 100 bytes was the size of my block, but now it should be 8K, but it's 100 bytes. And let's say the size of my record is 40. Then the blocking factor is 2 records. I can stick 2 size 40 byte records into that 100 byte block. And there's 20 that's just leftover slop. All right, that just gets wasted. But that's how you do it. So you don't span. You don't like say, well, I'm going to use that 20 and split the third record between the 2 blocks. No. Every record belongs to one and only one block. All right. Record. When I'm saying record, I mean a tuple or a row in the table. Okay, I hope that makes sense. So how would you organize the records in storage? So you can basically do it in 3 basic ways. You have 3 different choices here. You can do it as a heap, and heaps are kind of nice. I mean, heaps are kind of like, that's how that's how main memory is organized. You just kind of say, well, here's the pointer to the next available spot. And if you tell me to store something, I'll just stuff it there. And then I'll have another pointer, to the next spot in memory. And then if I have to take something away, I can just kind of do some pointer. I can kind of wind up doing pointer surgery, and then I'll have some kind of space that I can just then reallocate to the heap. Okay, so ordered though is usually how you're going to do it inside of the database. All right, so records are stored in some order of the values of one or more attributes. Okay, we'll look at that. These are very low level types of way of organizing. We'll see that databases have, just to kind of tell you what's coming up here. Databases almost universally use what's called the B+ tree. All right. So has anybody ever heard of B+ tree before? So it's kind of like a generalization of binary trees, but we'll come to those. That's what we're going to cover in this lecture today is B+ trees. So B+ trees have been, I think this Knuth was the one who innovated it. Donald Knuth. If you guys have heard of him, it's a big computer science. It's kind of like one of those basic algorithms that was discovered a long time ago, but there really is no superior to it. So B+ trees is how these will end up getting implemented. That's what databases are going to be using, B+ trees. That's the main indexing method. But we have some other methods like hashing, and we'll see hashing coming up in certain ways. But I'm assuming you guys are all familiar with a heap, an ordered kind of like tree structured like a binary tree, and a hash. All right, so let's look at the sequential organization here. So what does it mean for records to be ordered on disk? So if we look right here, what we're doing here is we're ordering the records on the ID of the instructor. Okay, so this is like the name of the instructor. This is the department. There's their salary. And we have 1, 2, 3, 4 blocks. That's what this example is covering here. Okay, So the blocks themselves, then, just to make these so they order properly. Now, I mean, you could just say, well, we're going to have it so the blocks are next to each other on disk, but that's hard to kind of maintain. Instead, what we're going to have is we're going to have a block pointer. So this block here then points to this block, and this points to that block, and this points to that block, and this block. So you could actually go through this sequence if you wanted to have things ordered by the ID number. Then the way you would do that, just to kind of get them in the standard order, is that you would just do pointer following of the basic blocks here. And what that's also showing us that there can only be one. So this is down at the physical level, how things are organized inside the blocks. So there can only be one value that we're quote clustering on. So when you say what this file is here, this data file here represents. This file represents, it's represented by a set of 5 blocks, 1, 2, 3, 4, 5 blocks, and it's clustered on the ID of the instructor. So the actual order, the ordering, in terms of the block order and in terms of the internal order inside the blocks themselves, it's all based on the ID. So you can only cluster on one thing, right? It only, because clustering is like physically how it's being laid out on disk, right? So this again, so a lot of times one of the main questions is, what are you clustering on? And usually you cluster on the primary key, but you don't have to cluster on the primary key. You can cluster on other stuff as well. So that's a choice that you have of what you're going to cluster on. So again, cluster is how you're going to order it on actually physical disk. Okay, so so we can have some empty blocks here. They're not so filled, but all is good. All right, so now indexes. So what we're going to find out later is that you have like the physical, like you have like the organization here. I'll show it here of the actual file. This is the data file. What we're going to see is we can actually build something on top of that, which will then facilitate. Like if you want to say, give me the instructor with. I mean, if I said this, if I say, give me the instructor with identifier 45565, that's right here, right? Now, what you would want to do is you would want to be able to just go directly to that rather than like going through and doing the big O N. I mean, if you say, give me the number of instructor with 83821, a naive way of doing that would say, okay, and you just walk through the full file trying to get to it. That would be dumb, right? That'd be big O N when we know we can do it in big O log N, right? And then when you say log N, in this case, we can say log base giganto number, like log base 255 of the number of blocks that are represented. So in other words, it becomes very, very rapid if you have this very, very bushy over this very wide tree. And that's what we're going to see B+ trees actually do exactly that. All right, so indexes now. So when we build these indexes that are going to be kind of over this kind of, we have the physical layout of the file, and then we have these indexes that are kind of over those. We have some classifications. So one is to basically say, is it a primary or clustering index? So is it an index built over the attribute or the key or whatever you might want to call it, that we clustered the file on? All right. So that's going to be a primary index if it's doing that, okay, or a cluster, or what's called a clustering index. A secondary index is one which would be which is not over the order. So you could build an index here over this right here of what department, like, and then it would basically say, okay, this is the department. You could, the first step would be computer science, finance, whatever. So if it was computer science, it would point to this one, and it would point to this one, and it would point to this one, because those are all the ones that contain data for computer science. I think this will become clearer when I get into the examples. So that's a secondary index, or what's called a non-clustering index. And then we have a separate question, and that is whether or not the index is dense or non-dense. A dense index basically says there's an index entry for every value, every value of the search key which occurs in the table. All right. This will become a little bit clearer when I go through the example. So dense would basically mean that the index itself has every single value. So we might have every department is represented in the actual index. That would make some sense. A non-dense index or sparse index would just basically be a subset of the search key values. Now, if you think about this, it makes sense that you can have a non-dense index over the primary, you can have a non-dense index over the primary or clustering attribute or search key value of the relation, and only that one. So non-dense only makes sense when we know that the actual layout of the file is on the order, is following the order of the search key value of the non-dense index. It only makes sense. So you can never, ever, ever have a non-dense secondary index. If you think about it, it's impossible. It will never work, right? So there's 4 possible combinations here, and one of them is absolutely ruled out. So there's only 3 possibilities. You can have a dense secondary index, you can have a dense primary index, you can have a non-dense primary index. Now, which ones get used most of the time? What is like almost always being used? You almost always have a non-dense or sparse index over the primary key, because you can, and you have a dense index over secondary keys or non-clustering keys, because that's the only way you can do it, because you must, right? If you're going to have an index over that. So I hope it makes sense. I mean, you know, it's all very rational, but sometimes maybe the terminology it can be confusing. I find that sometimes it takes a while to get these things. All right, so this right here is just kind of an example of a sparse index on the primary key. Okay, and that would basically say that here we hit if we want to search for the person numbers or the identifier numbers of the instructors, and we want the one that has the value of 76,543. We basically say, well, is 76,543 greater than that but less than that? No. Greater than this but less than that? No. Greater than this, less than that? No. Greater than this, less than that? Yes. Therefore, let's follow this pointer, boink, boom, and then we find the block where this is, right? So now the key question here, of course, is how many blocks did we have to bring into memory? So let's say this whole thing, including the index, is sitting out on disk, and we want the instructor with the identifier 76,543. Well, the first thing we need to do is we need to pull in the actual index block. So this is also in a block right here, this index. So we got to pull that in. That's one block we pulled in. Then we come here, we do like the simple calculation, and we say, and then now we need to pull in this block here as well. So we get 2 blocks. All we need to do is pull in 2 different blocks, right? And then we find the data, as opposed to being stupid and going, you know, sequentially through. That would take 1 block, 2 blocks, 3 blocks, 4 blocks. All right, so we'll see it gets a lot better than that, but that's just to kind of get to warm with the intuition. All right, so what are we looking for here? Okay, good. All right, a dense clustering index. Okay, so now we're going to talk about a dense clustering index on the, let's see here. What do we have here? I'm not really sure if this is the way I want to show that. I want to go over to here. Wait, a dense clustering. Okay, notice here, if I said this is the file here, if I maybe someone can answer this, but I don't know if we have the time. But if somebody can just do it quickly, that would be great to kind of make sure that I'm not losing people. Well, I'm not losing people in terms of numbers at least. All right, what is this? If this is the file here, if this is the data file for the instructor relation, then my question is that what is this clustered on? What attribute is this clustered on? Before, this was clustered on the ID number, right? Because we see that it starts out lower numbers, they climb, then it goes to the next one, they're still climbing, right? That's the way it's clustered on ID. This one, however, is clustered on this is clustered on the actual department. All right, so what does this show us? Why do we even show this example here? The reason why we show this example is because you don't have to cluster on the primary key. You can cluster on other attributes, but you can only cluster on one. So when you recluster a relation, it's going to reorganize things on disk. All All right. So now, does this make a difference for performance? Yes, absolutely. And this actually, you might wind up doing at one point or another if you really want to optimize a certain type of query. All right. Here's what I think is a bit better. This is more realistic. This is kind of more how it happens, the way it works. Is that what we have is we have the first of all, this is a block, and these are all blocks as well. Although, well, basically, here's the file itself. The file itself here is clustered on ID. And then what we have here is now we have, it has to be dense. Remember, it has to be dense. We have a dense index that's built over the this table here, where what it does is it's organizing things in terms of buckets. So what it's doing here is it's basically saying that if you want computer science, then you go to this bucket right here, and inside this bucket here, we have a pointer to this block, and to another block, right? And all those pointers, then what those do is they're basically showing this is basically a bucket file here, and what those are all doing is they're showing where to go to go to blocks that actually have that value of computer science, right? So in a worst case, it's a terrible situation, because in the worst case, what we have is we have basically a pointer out to every single bucket. So I mean, it's possible, not maybe likely, that computer science is represented in every single bucket. So this is why secondary indexes can sometimes be counterproductive, or not give you much at all. Now here we're climbing toward the actual idea of a B+ tree here by showing that we can actually stack these hierarchically. The actual indexes wind up becoming trees, which is kind of an obvious thing. So that's what brings us to B+ trees. So B+ trees is the way this gets done in PostgreSQL and any other database at this point. So this is, everybody's using B+ trees. One thing to keep in mind, though, it's kind of interesting, is that when you look at B+ trees and their implementation on this in an actual system, I think I heard at one point PostgreSQL has like 7 or 8 different implementations of B+ trees, but it has 7 or 8 different implementations inside of its system. And we'll talk about a little bit why that happens a little bit later on. But what it's basically showing is it's showing that these things get very, very specialized and tuned to a particular use case. So even PostgreSQL doesn't have a single B+ tree implementation. It has 7 or 8 of them. It might even be more by now. All right, so B+ tree is an important one. So let's just talk, let's just review quickly, because we all know what a binary search tree is. So if we're looking for instance, the 3 letters that are basically JUL for July, then you come here to the root and you say, well, you go this way, and then you compare it to here and you say, oh, it's going to be less. You go here, compare it here, and you go less. All right. So this is our basically B+ tree, or binary tree that we've all seen from basic computer science 101. So what's the problem with the binary trees? Of course, the problem is that you might be very unlucky, and it might just wind up being just you might have, you can have ON search depth, because it could be that everything's already ordered when it gets put in to be built. Let's see if there's an example of that. No, there's not an example, but there's no guarantee on balance. Worst case, it could be a order N search, right? I mean, I'm assuming everybody remembers that. And you're also doing a lot of pointer following, and each of these could potentially bring in a fresh block, this is not good. Okay, so B+ tree. What's the B+ tree? It's a balanced tree, so the length to each leaf is the same for all leaves. All right. So we're gonna, and we'll see how we do this in a second. We force balance. And that also, by the way, forces that we're going to wind up getting log-based access, because we force the balance. All records, so all the records are stored at the leaves. All right. And this can be a little confusing. So what this basically means, it means there's 2 types of nodes in a B+ tree. There's the internal nodes, which hold index values and pointers to different index blocks, it has pointers to blocks basically. And then we have the leaf nodes, and the leaf nodes are just the file itself. These are the records all strung out. Okay, this is for a primary, this is for an index that's built on the primary key, or it's a, how do I put this? It's it's the one that's built over we're going to try to focus on the B+ tree. That's the clustering, that's basically a clustering index that is which is non-dense. Okay, so the sparse clustering index is kind of our default case for a B+ tree. I hope people follow what I'm saying there. All right, so the internal vertices contain the index only. So the internal vertices are part of the index, and the leaves, the records are at the leaves. Okay, so the advantages are that since index fields are typically much smaller than the record fields, so the index fields wind up just being the search key value and then pointers going out, then we get this extreme fan out. We get this extreme fan out in terms of the structure of the tree. And then so it basically implies that also, since it's so you can pack so much into you can pack so much into a block. So all of these things, every node, both the leaf node and the index node, those are always fitting into exactly one block. All right, they're always based on the size of the block, and they're always, we try to fill them up as far as possible. Then the leaf vertices, maybe we'll get a picture here. So here's a picture where we can visualize a B plus tree. All right, so what we have here is we have the nodes in green are the index nodes. All right, so these are all the internal. So if you can see, the depth here is 1, 2. It's a 2 depth. The depth of this B plus tree is 2. All right. So if we were going to be looking up, if we wind up, let's say that we have the root here in memory already, so that we already have that. The root here is already sitting in memory, and we want to look up 33. So that means that we're going to say, oh, well, is 33 less than 35? This is the search key value. Yes, it is. So we grab this block. That's one more block. So that's the first block we took from memory. I'm sorry, from disk. So we took that block and we brought it into memory. All right. Then we basically said, okay, is 33, okay, it's greater than 24, but less, okay, yeah, sure. So we follow this way here, and then we bring in this block. So we basically, if we assume that the root is already in memory, it took us 2 blocks to locate the record, right? We just had to get 2 blocks. The order of these things are basically how many, the order of index basically is how many search key values can fit into the index. So we have 1, 2, 3, 4, 5, 6, 7, 8. Actually, I was wrong. It's how many pointers there are. So it's 8 plus 1. It's 9. So the order is 9. And then this 4 here, that's something that's a little bit special. What the 4 is basically saying is it's saying that each of the non-root internal index nodes, okay, which are this one and this one, have to have at least 4 values within them. Otherwise, if they only have like 2, then they need to be merged together. So the constraint is we never let it go below 4. All right, it never goes below 4 search key values that are in an internal node. All right. So what this means basically is it means that you when you do inserts, if you're doing inserts and then that requires, you can't. I mean, if you do an insert, like if I'm inserting into this one here and there's already 1, 2, 3, 4, 5, 6, 7, 8 values, then if I put another value in, then it's got to split because you can't, there's no more room in the block to fit it. So you got to split the thing. And then when you split it, that means that you're going to maybe, there's a lot of different ways you're going to handle the split. I mean, that's why PostgreSQL has all these different implementations, because there's a lot that, how it handles the splits, how it handles splitting and then potentially growing the depth of the tree versus how it deals with deletions and potentially shrinking the tree. That winds up being the fiddly bit that you kind of have to kind of tune to whatever particular use you have of the B plus tree. And there's an infinite number of those possibilities, but that's where the intricacies come in terms of the implementation of these things in systems. All right, so notice here that the non-leaf vertices, all right, so, well, we'll see here when we go to this one here. Convention for index paths in B plus tree. So this is just telling us kind of the conventions about how we navigate this thing if we're, say, looking for the value of 33. It should be pretty clear in itself. All right. Time. So this is just kind of repeating what I was saying before. This is just gives you a little bit more formalism around those policies. So when you insert, for instance, here, so consider inserting the record with value 20 in the above tree. That's going to be pretty easy to do because all it does, Well, it's a non-dense index, so all it does is it just goes down and it finds it down in here, and it just stuffs it in there into the leaf node. So we just put the new record in there. But what it's showing here is if we continue going on with his insertions, then what you can get is a situation like, and I think in this case here, we're going to insert the record of 28. Okay, that's fine. Let's see. I think that what it's getting at here is that we could, if we wind up inserting at this level here, we're going to have to split that node. Anyways, you can study these slides. It's not. It is all pretty straightforward in terms of, I hope that you get a sense of what the logic is of how any algorithm that does a B plus tree has to kind of manage this kind of stuff. And likewise with deletion, that you get this underfill situation where you're going to have to shrink the size. So this is an example here. If you delete 38 here, so you delete 38, it's going to make it so that there's no way to reorganize the thing, so that there's only going to be 4 search key values in this internal node. And in this one here also, so basically what this is going to necessitate ultimately is that you shrink the whole depth of the tree. All right. Now, I'll talk a little bit more about that later and about how you want to have. So I'll just say it right now. In real implementations, what they do is they deal with like kind of momentum issues. So here's like a terrible day for a B plus tree. Because the cost of doing like growing the size of the tree or shrinking the size of the tree, that's expensive. So if I had it so that I was just on the cusp of needing to kind of go to the next level, needing to grow the tree, so it was very, very dense, and I added another value in, and that made the tree kind of, grow another level. And then I delete something. So I say insert, delete, insert, delete, insert, delete. And I'm just at this boundary, this cusp of the size. A bad day for a B plus tree would be that requires a rebuild in every time I do that. What you would rather have in your algorithms is a little bit of momentum built in, so that basically, if I'm shrink the thing, now I should have it so that it will always try to figure out a way to keep things at the same height, and let a lot of things fill in before it has to actually increase the height again. So you would want to avoid that thrashing behavior of back and forth. And a lot of the algorithms deal with that. It can be somewhat complicated when you implement the things, but that's kind of the reason why the B plus trees get complicated, because you don't want to have that kind of that little horizon effect where you're kind of going back and forth from depth 7 to depth 8, back to 7 to 8, 7 to 8, just because you're doing inserts and deletes on a single value. You'd like that. You'd rather have it go from 8 down to 7, and then you add more stuff in. It just has this kind of thing where it just fills it in, so we don't hop back out to 8 again. All right, I hope that makes sense. All right, so the sequential access, so this idea of going through things in order, and in particular in the clustered order, that can be facilitated by just having front pointers on the leaf nodes, so that they point to the next leaf node. So that's kind of a nice way just to kind of, if you just want to read through the file in one big sequential scan, you would forget the index and you would just start here and just follow through the whole set of blocks that determine the file. All right, so what this is right here, I don't want to get into this so much, but we will get into it in recitation, because this is going to be kind of this. I think that by doing a little bit of math, a little bit of arithmetic and kind of mathematics around this, this makes it so that you really kind of understand the concepts better. So what this basically has to do with, making some assumptions about like what's the in this case the block size, what's the size of a record, how big are pointers, how many bytes are necessary for internal key, and then what are the total number of records we need to account for. And we can do this under certain kind of assumptions of like the maximum packed assumption and then the minimum packed assumption, where we're only, so based on the order, we have it so that things are as thin as possible in the internal nodes, or we can have things are filled in as much as possible. And we see that what it winds up being the necessary height. And this can give us a bound on what the actual height is of the index. And in recitation, I'll give you guys a real example that will be based on PostgreSQL. So basically from that, you should be able to determine for this particular imaginary relation how big the indexes are. And we can maybe try to see if we can verify that under the hood in PostgreSQL. That'd be kind of cool. But anyways, what this does is, again, these are just some of the parameters. Now, the business for B plus trees, what keeps it so that we can have them always balanced is that we have an order basically that says, here's how many search key values need to be in non-root internal nodes, the non-root internal nodes. And those are the, one second here, I just got it. Okay, good. You guys can probably re-listen to this on a recording. The root node can actually can have just one search key value. So that is the flexibility in the formalism that allows it so that everything is the same distance to the leaves. That's how you can get the perfect balance, because something had to give. Otherwise, a binary tree otherwise would just be a special case of a B plus tree. But so in other words, you could wind up getting the imbalance. But the condition that basically you account for you have it so that you can always guarantee that it's a perfectly balanced tree. The reason why you can do that is because you relax the conditions on the root node. All right. So this is just kind of gutting it out and kind of being able to do some of the calculations. So the slides will give you enough for that. All right. So we'll talk about secondary search keys for B plus trees. So the B plus tree can only be ordered on one attribute, of course. A second index, if created, the leaf vertices can contain either a key or else a pointer identifying the actual record. Okay, so one way that's kind of elegant, I'm not really sure how PostgreSQL does it. I should find this out. One way of doing it is what you can wind up doing is inside so on a secondary index, remember I talked about a bucket file? Another possible way of doing a secondary index is that what you have is on the leaves of the secondary index, what they basically have is they have if you have a primary index that's you have a primary index that's on the primary key, then what you can do is in a secondary index at the leaf nodes, you can just hold the actual key value, and then you reuse the other index when you're actually trying to kind of solve for these things. So that's the elegant way of not having to have special implementation of a bucket file. Maybe I can say, maybe we'll kind of discuss that a little bit more when we come to recitation. In fact, we will, because what I'll do in recitation is I'll have you guys work up a paper example where you're going to build a secondary index as well. And I'm going to specifically say that what you're going to represent in the leaf nodes in that secondary index. And what it's going to wind up being is it's going to be the, I'm going to find out actually how PostgreSQL really does it. But I think what it's going to wind up being is it's just going to wind up being the key value, the primary key value of the records. Okay. All right. So so that's B plus trees. So that was kind of a whirlwind tour of B plus trees. But this is essentially is what you're using. Now, when you look at the B plus trees, like when you look at let's see, if we look at this example here, maybe like this queue here, this is the number of keys this is the number of keys in this particular case here. This is the number of keys that are in the internal index nodes. So what this basically is telling you, now Q could be higher than that. Q can be up to, I think the other example might be Q equals to, let's see here, Q equals 51 there. And then I think it's going to be Q equals 103 in this case. Anyways, let's say the Q, so that's the fan out. That's the fan out that's happening in the internal nodes. What that basically means, it means if you have 1 million records, then the number of, and you want to do a search and find just one particular record, that means it's going to be log base, let's say Q is 103, log base 103 of 1 million. That's how many blocks you're going to need to be brought in. And log base 103 of any large number is a pretty small number, actually. So you wind up really, so it's not a binary tree, it's not log base 2, it's log base that fan out Q. So in a real example, we probably get something like log base like 350. So log base 350 of 2 billion is a pretty small number, actually. Okay, so it winds up just showing like the power of this kind of fan out and the speed that it gives you when it comes to locating records. All right, so what do we have here now? Let's do this really quickly. Since PostgreSQL that we implement doesn't really have much support for bitmap indexes, but bitmap indexes are what they wind up being is a bitmap. So it's like this. It's like, let's say, let me just line it up this way. Let's say that we had, let's say that we wound up having a big table of all the people who lived in Sweden, right? And let's say that what we have for them is we have in their bokföring, we have what land do they live in? All right, what land? So I don't know, how many lands are there in Sweden? There's Västerbotten, is there like 20 something? Can someone put that in the chat so I can see the people are still hearing me? How many lands are there in Sweden? I mean, how many lands? I think it's like 23. Maybe I can do a Google search. Does anybody, so it's like we have Stockholm land, we have Västernorrland, we have Norrbotten, we have Västerbotten. What else do we have? We have a whole bunch, right? But not that many. Let's just think of another one. Let's think of like, that one's kind of controversial. But let me just say, okay. All right, there are 21. That's maybe a better example. 21. All right. If there are 21 of them, okay. So what about building? Let's say we're gonna we want to build a. Let's just keep it simple here. Let's say we want to build a index over. We want to build a B+ tree index. Keep it a secondary index over the lands that people are in. So that what we would want to do is we want to say something like, give me the people, and then certain like an age or whatever, between this persona number and that persona number, which is age implicitly, who live in Västerbotten. Okay, so we're going to build a secondary index on land over all of Sweden's 10 million population. All right, so what does that tree look like as a B+ tree? It doesn't look that good actually, because it doesn't take long until it's just going to be this giant, it's going to be a really bushy tree at the very, very top. It's going to start out, and then it's going to basically say, all right, it doesn't take long until everything underneath it is just one giant span of persona numbers of people who live in Västerbotten or some other place. So the index, I hope people see, the index won't give us much, because all it will do is it might, I mean, you could argue maybe there's ways you would do this. You could partition the table into the lands, but let's do another one. Okay, and let's just say gender, all right? And let me be, because I don't want to, cause any trouble. So I'm going to say there are 3 genders, all right? And then maybe we say 4, I don't know, but I can't say 2, but let's say 3 or 4. How many genders are there? I'm not really sure. But let's just say for purposes of argument right now, there is male, female, prefer not to answer. All right, so we have 3 of them. Okay. Would it make sense to build a B+ tree index over all of Sweden on those 3 values? Would that make any sense whatsoever? Would it give us any speed up really to speak of? Do people see why it would be kind of stupid to build an index when there's only 3 values? I mean, let's build an index over persona number. How many, we got 10 million people. How many different persona numbers are there? Well, there are 10 million. So it makes sense, right? There's actually some kind of work going on in each of those choice points inside the internal nodes of the B+ tree, right? Okay, I hope that people understood that. So, when we look at gender, what's an alternative approach to gender? Well, the alternative is called a bitmap index. And what that basically means, it means we're going to build an index. It's going to be this giant vector of 0, well, let's say of 0, 1, or 2, which encodes the different genders. And we're going to run that thing out. That vector is going to run out for 10 million values in a giant long sequence. All right. And then all we do is basically say that, well, if you want to say, give me the person of this gender who live in this, who have persona numbers between this and this, all you do is you use the B+ tree to get that sequence, and then you just run along that sequence and just doing a check on the bitmap index, true, false, all the way out. Okay, does that make sense? Okay, so bitmap indexes, actually bitmap indexes, like something like Redshift uses a lot of bitmap indexes. Bitmap indexes are kind of the way to go. So what you also do with bitmap, so this example here in the slides is a bitmap index where you're kind of, you're doing like an encoding, bitmap encoding of people's age ranges. All right, so that's what's going on with that. So bitmap indexing is something that really hasn't found its way in to PostgreSQL like standard implementation, but it certainly has found its way into Redshift. Okay, so bitmap indexing, you just keep that in mind as an alternative technique. Now, hashing. So hashing was, speed, I can do hashing in 2 minutes here. Hashing is like something that was, you could argue, oh, well, why don't we just have a hash index instead? But the truth is, because the hash index is, it's like, well, how does hashes work? The way a hash works, it'd be like this: we put a Persona number in, we compute a hash on it, and that gives us the address of the bucket where that person is stored. Okay, all right, all right, fine. But it doesn't quite work that way. What happens is you take the first certain digits of the Persona number, or you do the hash, and you take only the significant bits of the hash, so that more people, so that you can have more people fit into the bucket than just for that one particular Persona number. So the size, so I hope people understand the idea behind the hashing there. So databases have developed hashing, but no one uses them anymore for the primary storage. You could still do it in PostgreSQL if you want, but no one does. Because the reason is because, sure, with such a high log on the B+ trees, it doesn't really matter. B+ trees can give you this kind of direct index. It simplifies the implementation. But hashes are used in query processing, so that's actually important. So hashing is used, but it's used more kind of for intermediate results when you're doing query processing. For instance, like determining whether or not there are duplicates, or determining, there's a way that you do hashing to do joins to find the matching tuples on a join. The hash join, which is really kind of a fundamental operation. So it does make sense for us to look at hashing a little bit, but just consider it to be something that that we're doing over intermediate results, not on the actual tables themselves. So the idea behind the hashing, of course, is that you give the key, and then you can grind out through a hash function. You can get a bit sequence, and then you can basically use only the top significant bits to find a bucket. And what extensible hashing does, which is really cool, is that it allows you to in a very kind of, you can, as the buckets fill, you can wind up just looking at and then refiguring the buckets kind of only at the leaf level. And so you can have it so that you don't have to recalculate. Basically, everything kind of can still be in place. But you have this index here, which tells you how many digits you're looking at. So basically, you just have a, how do we do this here? You have this index, right? You have the main hash index, which basically will point you to the different buckets based on the number of values in the depth. Let's see if I can show an example here. So now see, we've extended out to 4 significant digits on the hash. So you guys can study this. It's pretty straightforward, but it's kind of a nice technique. And again, it's used, but not used, but used more for intermediate. If you go to the, I think that what we'll wind up doing is, I'll probably come back to this part here, but I want you guys to study. So you have to do it for recitation anyways. But this right here, we'll probably return to this a little bit to discuss how you actually declare and then use the deal with clustering and deal with indexes in actual SQL and PostgreSQL. And again, recitation 2 will kind of force you into learning this, where you're actually using these concepts over a real PostgreSQL database. So, all right, guys, that was fast, but I'm glad we kind of made it as far as we did. This is perhaps not the most exciting stuff on earth, but it pays to know. As you'll see, it pays to kind of know and have some awareness of this stuff. All right, guys, are there any questions? Because it looks like we're time is up for today. Again, this is Friday. Tuesday, we continue with this and we go into query processing. And then next Friday, we're going to do group meetings. And then the Tuesday following that, we have recitation number 2. Okay. And also groups, I really hope you guys are kind of starting to think. I'm not getting that much action on the group stuff, but it'd be nice if I got some more kind of ideas kind of bounce my way. I hope that people didn't get turned off because I gave some reactions that were just like, well, you know, try to kind of extend things a bit more with some of the ideas that came in. But in the end, we'll get projects. We'll get some cool projects going. So, okay. All right. Well, if there are not any questions, then thanks for all that. So we will see you next Tuesday. All right, and I'll just stop it here.